Okay, so the last class basically we had started discussing about the SIFT method, which is basically stands for, what does SIFT stand for? Hmm? What is the full form of SIFT? What was SIFT basically? What were we discussing in the last class? Broad idea. Hmm? Orientations or scale? So mainly we saw that Harris corner was okay with orientation and other changes, but with respect to scale change, Harris corner was not Harris response would not do well for finding corners. So we were basically discussing how to find features which are scale invariant, irrespective of change in the scale. Also, you should be able to repeatedly detect the key points. So SIFT was basically stands for scale invariant feature transform. S for scale invariant feature transform. And these are the 4 steps. So we in the last class we discussed the first 2 steps, which basically is for feature point detection, and the third and fourth are for basically describing that feature. So for feature point detection, basically the first step was scale space extrema detection. What was this step meant for? What do you mean by scale space extrema detection? What do you mean by scale space? So our thing was basically we were trying to find corresponding scale size in different images which have been scaled by a certain factor. So to find out the characteristic scale in each image independently, we needed to generate a scale space, so that we generate the response of a function at different scales, and at each scale then we try to find out the maxima. Why maxima, why extrema detection? Actually it could be maxima or minima, but why we were trying to find out the maxima? Because it can be well localized. It can be normally the function that we'll choosing will be having only just one extrema in the entire response. It will have just one extrema, either maximum or minimum. So we would that's why we would choose the extrema point, and that's what we were doing by generating scale space. So the main purpose was to basically make it scale invariant. So once we do that, then we could localize the key point, and we saw different things that we were basically doing. So we generated different scale space, and normally for SIFT, instead of Laplacian of Gaussian, we would actually use difference of Gaussian. And basically this is what we saw we will get. So after we detect extremas, we'll have to get rid of some points which are either of low contrast, so by putting a threshold, and also we have to remove points which are lying on an edge, because this is not explicitly handling the edge case. Harris corner was explicitly avoiding edge response. Here we were not using anything, so there are possibilities that we may get points on edges. So we may try to filter out those also to get our key point locations. So once we have got the key point locations, then then the thing is how to describe them. In the Harris corner, we had no method to describe the feature. Here we have in SIFT we have a method for describing that feature point. And the main idea is that while describing, we have to make a trade-off between two things. We want to make our descriptor as invariant as possible while we move from one viewpoint to another viewpoint, but at the same time we want it to be distinctive enough so that it does not match to similar points. So that trade-off has to be maintained, which is a very sensitive trade-off. We'll see. So how SIFT procedure actually does this, we'll try to discuss in today's class. So before actually doing the description, it also tries to uh, handle the orientation problem. Harris corner, as I said, was rotation invariant in the sense of, but even for describing our key point, we'll have to we have to make it rotation invariant. So I'll just explain what basically it means. We have to first make our descriptor invariant to rotation. Whatever descriptor we may choose, we'll see what we will choose finally. But we'll have to make it rotation invariant to rotation, because in one image may be in one direction, another image the patch may be rotated by certain degree. So the method which SIFT paper takes it so let us say there is a key point here. So within a local window around that key point, it tries to find the dominant direction of the gradient. So for example, if in this patch, if we see the gradient are moving in the gradient changes in vertical direction. In this patch, the dominant gradient changes in the diagonal direction. So the idea of using this dominant gradient direction is we'll describe our features relative to this dominant direction, so that every time, so irrespective of whether the patch has been rotated or not, the descriptor will always be in reference to this direction. So we'll make it invariant in that sense. So like we'll make it new north. So if you have north, south, east, west, so always even if this patch has been rotated in other things, then let us say in the new images the image was slightly rotated by 45 degree, then the dominant gradient direction will be in this direction. So now our descriptor will always be with respect to this you will basically unrotate it. We'll make it, let us say, again back to, so we'll make it again back to this, and then we'll describe it. So in that way we'll try to handle the invariance to rotation. So for doing that, basically we'll be calculating in this local patch our gradient magnitude and direction. We can use any filter that we have used, gradient filter like Sobel and all that. So you can see this is just the similar. They did not use direct filter, they just use the difference of the right forward difference and left difference, and the angle using the tan inverse. So I know how, I hope everybody is recollects how to calculate the gradient magnitude and orientation. So for each pixel in this patch, we will calculate this gradient direction and magnitude, and then we will create an histogram. So in that patch, now different locations may have different gradient directions. So we can distribute them in a histogram from starting from 0 to 360 degree, and we can create a bin of certain numbers. They have actually selected 36 bins. How they selected this, we will see later on by experimentation. So basically, they divided this range from 0 to 360 to 36 bins, so 10 degree rotations. Now within each bin, so there are different directions of gradient. We'll basically distribute them in the bin of this histogram, and then of course the one which is the dominant, which has the highest frequency, that will be our dominant gradient magnitude. The reason why they do this way is why not simply count it. The thing is, they actually do some kind of a smoothing also. So actually they do some kind of a smoothing. So in that way, for example, in this patch, let us say these are like gradient directions. So most of the gradient directions are in this. So our dominant gradient direction will come out to be somewhere around in this orientation. So now there may be, if more than one beans are at equal level, let us say there is not just a unique bin which has the highest count. There are more than one bins which are at highest count. Then what what should be done? So they do some kind of smoothing, as I said. So they do some kind of a smoothing here to ensure that um, slight displacement does not actually make that changes. The other thing is that even if there are other bins which are almost 80% to the max bin, then they will create that many descriptors. So if there are, let us say, three bins, three angles which are basically almost equal to the max or at least 80% equal to the max, then they will create three distinct three separate descriptors with respect to that direction. So in that way they will handle the even if there are more than one dominant directions, they will basically they will create a duplicate kind of thing. It will not be duplicate because the reference point will be changing, but basically for each that patch they will have multiple descriptors. So what uh, so now whatever key point now that we are basically describing, it will be invariant to translation xy, it will be invariant to scale, as well as now it will be also invariant to orientation. So translation is anyhow we had seen it's normally does not affect scale. We have taken care of by using the scale space thing. Now finding the dominant orientation and then making that as our new reference direction, we'll also make it invariant to rotations as well, or the orientation thing. So this is what I was saying, they will actually do a smooth histogram and then assign the dominant or the canonical orientation at the peak of the smooth histogram. So before we see the actual descriptor, uh, the normalization is done like this. So we'll rotate the window to the standard orientation. So let us say we always, every time we always want it to be in this, the dominant direction to be in this things. So we'll rotate this one back to the standard orientation, so that every time our descriptors are always with respect to that. Canonically here in this sense means dominant orientation, or the major orientation here. So we'll rotate the window to the standard orientation and we'll scale the window size based on the scale at which the point was found. So let us say it was found at some scale. So we will also accordingly will either will fix the window size for every feature point. If the scale was lesser than that, we will basically resize it accordingly. If the scale was higher than that, we'll downsize it, otherwise we'll upscale it. So the scale also we will keep fixed, as well as the orientation also will fix. We'll keep on standard orientation, and every other key point we'll try to normalize it to that fixed standard orientation as well as the scale. So now to describe our key point, as I said, we need to have a trade-off between these two things. We need to be highly distinctive, as well as also it has to be invariant to the possible changes in viewpoint and illumination. So what do you think, how you would like to describe a patch around a key point? What kind of, what should we use as a descriptor for matching purpose? Because later on we'll have to match whether this key point is the corresponding key point in this. So we need a descriptor here. So with what thing we should use to describe that patch? Should we use straight away the intensity values in that? Hmm? So normalize intensity values. Okay. Any other session? In that sense, you're saying basically using a normalized template of this. But as I said, it won't, then matching will be a problem because it won't be invariant if the template intensity changes, other things, and it may not be highly distinctive also. Yeah. Hmm? Hmm. Hmm. Then the distinctiveness, you will be compromising on the distinctiveness. If you histogram equalize it, okay, let us say you histogram equalize, so then what will be the descriptor that will you still use? You will use the histogram itself or the intensity values? Okay, so it turns out the main descriptor that they will be using histogram of gradients actually, rather than just the intensity value or histogram of intensity value. They actually use histogram of gradients, and then there are many details here that we'll just try to uh, uh, surf through, not too much, will not go zoom into too much detail. So um, so here I'm just showing you a grid of 8 by 8 pixel, let us say here. So these are just pixel locations, and the arrows are basically depicting the direction of the gradient, and the length of the arrow is depicting the magnitude of the gradient. So for each pixel, you at each pixel location you will have certain orientation as well as the direction of the gradient, and that is being represented here uh, in this case. And the descriptor will be formed using a histogram of these gradients, and it will be weighted by a Gaussian window. So again, we will do some kind of smoothing here, and the purpose of smoothing is just so that if because as we said, when we are going to detect few points in our new image, it may not always happen that it always lands precisely at that same location. It may be shifted, translated little bit here and there. So little bit shift should not make so much changes in the descriptor. So smoothing takes care of that. So when you do smoothing, when you do little bit shift, the change is not as, if you, let us say, even if you change 2 pixels here and there, because the majority contribution is going to come from the center one, not from the outer one. So if you shift little bit here and there, that effect will be little minimized. And of course, our histogram will be weighted by the magnitude of the gradients, which I already showed by the length of the arrow. So the magnitude of the gradients will be used. Uh, so the exact description will be like this. So the descriptor we will use basically, for example, in this 8 by 8 grid, let us say we will divide it. Let us say I'm just showing you here. Let us choose 4 by 4 regions. So we'll have one 4 by 4 region here, another 4 by 4 region here, and third 4 by 4 region here, and so on. So within each, so this is the our patch. Let us say we'll grid, or we will basically divide this patch into another 4 by 4 regions, and within each region now we will create a histogram. So this is depicting a histogram here. So histogram uh, will have 8 bins. They actually, how they came up to these numbers, these parameters, will show by experimentation later on. So they will distribute these orientation of the histograms in 8 directions, and we'll get one histogram for one 4 by 4 region, similarly for another 4 by 4 region another histogram, and so on. And these histograms, as we said already, they will be weighted by magnitude and the Gaussian window. Then they concatenated all these, actually they used instead of 8 by 8, I'm showing, actually they use a 16 by 16 neighborhood at every key point. They used a 16 by 16 neighborhood. So within 16 by 16 neighborhood, actually they got 16 such regions. Here I'm showing only 4 regions, but they will actually get 16 such regions. uh, so all these 16 histograms, they just concatenated into a single long vector, whose dimension will come out to be 128. Why? Because each histogram is of 8 bin, so it has 8 values, and there are 16 histograms. So I think it turns out to be 128 values. So that means our patch, the descriptor of our patch will be a single vector of 128 dimension, which will basically be just having the this histogram of oriented gradients concatenated in that way. So the one thing to be first of all, we are using gradients. So first of all, we have already, so why this is going to be both invariant as well as distinctive enough. So as we said, we have already normalized it with respect to orientation and scale. Then we have also, instead of taking the intensity value, we are taking the gradient value, because the advantage with gradient is now even if you multiply it or add it, the gradient does not change so much. Multiply it will change, but at least additive and all those things won't change. And at least the orientation won't change that much. And we are actually using orientations also information here. So this will be quite distinctive enough. But at the same time, we are also ensuring that if there is small slight changes, the descriptor should not change that much. So that's why we are using a histogram value rather than exact values, because histogram is kind of a global thing. Rather than taking the exact patches, we are actually using just a distribution within that. So distribution won't change that much when we change our locations little bit. So as you see now, the concatenation, the way they concatenate is this this first histogram will occupy the first part of the vector, then second histogram will occupy the second part, the third histogram will occupy the third part, and so on. So in that case, there is some spatial layout is being maintained, because the top left location is going to the first location, or the initial part of the vector. Similarly, the bottom most location is going to be at the end of the vector. So some spatial layout is being maintained, but it is not so precise, so that it's not, that spatial layout is not so precise that if you move our location little bit by few pixels here and there, your vector is not going to change that much. It may change little bit, but it won't change that to that degree. So the thing that I'm trying to impress here is that by doing this kind of descriptor, we are trying to maintain some trade-off between distinctiveness and invariance. So this is what I was talking about, smoothness thing. Hmm. Hmm. Yeah. No, if the image patch itself doesn't has, if you are saying it's just a square. No. If the object itself is symmetrical, so there is some more details here. If they try to clip the gradient magnitude to avoid excessive influence of high gradients. So as we said that we'll be weighting by the magnitude of the gradient. If some gradients are very high, normally they are going to dominate it. So to avoid that thing to happen, we'll just uh, clamp all the gradients. All the gradients which are greater than 0.2, we'll just clip it to 0.2. This again, these values are by experimentation only. And to reduce the effect of illumination, the entire vector is normalized to unit length. So it is like normalization. While so entire 128 dimensional vector will be normalized by its magnitude, so that it becomes a unit length. So the thing is that the magnitude itself doesn't matter so much. It is the distribution within that vector which will matter, not the exact magnitude, because the magnitude may change either because of illumination changes or whatever. So this normalizing to the unit length is also being done to reduce the effect. And the nice thing about this was why it became so popular, because the evaluation was done quite extensively. This descriptor was evaluated with several changes, and quantitatively they proved that actually it does work under different changes. So for example, they took several images in the database, and they subjected to different types of transformation: rotation, scaling, affine, stretch, brightness, contrast change, noise additions. They did all kinds of perturbations, introduced perturbations to the images, and then they detected the features and descriptors were compared before and after the distortions, and they tried to look for the stability with respect to these changes after location. And even for example, on this side we can see the different type of transformations that were introduced. Contrast was increased by some factor or increased by some factor, rotation was done by certain degree, scaling, stretching, and noise. So after doing all those transformation, what was the stability of our location and detection of the key points, and then matching the key points with respect to orientation. I think I should first discuss how they did matching. But what I'm going to show, what this table basically shows, that around 70 to 80% of even though you may introduce extensive distortions, you can still expect that 80% of the time you will be able to identify the same key point and also match it to the right one. I'll just come back to this again. Before we discuss the experimentation, how did they match the key point? Um, so you so we have used histogram things. Now you can take the Euclidean distance between two histograms as a similarity measure, or you can use a dot product between two histograms. There are different measures to see how those two histograms are similar. The one they use was the simplest. They use basically the Euclidean distance, minimum Euclidean distance between the two histogram. That's why actually they had to do a lot of normalization, because if you are doing some dot product or all things, maybe you don't have to even normalize it, because normalize in the sense at least the magnitude normalization you don't have to do that way. But they went for the simplest minimum Euclidean distance. So basically they took some images, found key points, and they stored them in a database for the training. For all the training images, they created a database of feature points, and then given a test image, they ran the SIFT algorithm for detection and then description, and then they try to match those key points from the database of the things. And for matching it, they use basically the nearest neighbor thing. So the one which gives the minimum Euclidean distance, that is the closest match. Now this can again nearest neighbor, that means you have to match, you have to basically compare with all. So if your database has 10,000 or millions of key points, then you'll have to do matching against all those things. So it may be little slow, so you can speed it up by using some algorithm like KD tree and hashing techniques. You can speed it up. They actually did it, and they speed it up by by a factor of 2 or 3 times. Again, I'm not going to go into details of this. But the other thing which is important is how did they add robustness to matching? Because what will happen, sometimes the one that you're trying to match may be a real match, but sometimes it may be a false match. False match in the sense, for example, that key point was occluded, for example, in our test image. So there is no real, there may be no real correspondence of that point. But because you are going for a minimum Euclidean distance, it will find some key point which has the minimum Euclidean distance. And you may say that this is the closest match or the best match, but it may not be a real match, or other that is the extreme reason. But even if there is not, the point has not been occluded, the problem is that some of the, as she was saying, there may be some symmetry in the objects. So some key points, they may be distinct key points in terms of spatial location, but the patch around them, they may be quite similar. So even if you rotate in all that, still the description of those patches may come out to be almost same enough. So even though you are trying to match, even though you have tried to ensure that your descriptor is quite distinct, but still it may end up matching the wrong key point. So to add robustness to that matching, uh, they use some kind of a trick basically. Instead of just using the minimum included, the best match, they actually found the first best match and the second best match, and then they took a ratio of the distance between the first best and the second best. So let us say d1 is is the the distance from the first best, and d2 is the distance from the second best. Then they actually use this ratio d1 by d2. Now what this ratio will tell us, if it is low or if it is high, it will tell something. So if these two distances are almost similar, then it may happen that because those are not too as I said, those key points may be similar key points itself. So you may not be sufficiently confident that your match is a good match. But if that key point is quite distinct, or the patch around that key point is quite distinct, then it is then the closest match, uh, the best closest match and the second best closest match will have a significant difference, isn't it? The best closest match will be quite close to that, and the second match would be quite some random, and that distance will be higher. Whereas if the key points itself are not so distinct, or if it is just a noise, or just was occluded, or some case it just landed at to some random key point, then the second best match will also be some random key point. In that case, the ratio of those d1 and d2 will be high, in the sense because both d1 and d2 will be comparable. So in that case, this ratio will be high. Okay, but still it does not solve the entire problem, uh, because as we said, we are trying to make this trade-off. So even when we are going to pick best match, and as we said, there will be lots of key points, and especially in your database, you will have millions of key points. And when you are going to match, there you cannot avoid wrong matches. There will be some outliers, either because the key point itself was not so distinctive, or it may be occluded in another image, so you could not find a good match. It will randomly land up to some wrong match, and there will be n number of problems because of which you may end up with a wrong match, and that we called as an outliers. So in today's class, we are going to just discuss the method that SIFT used to handle these outliers, but in the next set of lectures, 2 or 3 lectures, we'll see a more systematic theory or more systematic approach in dealing outliers in computer vision. Um, so this is this is just a sample image to tell you what is this outlier basically meaning. Of course, this image I have not taken from the SIFT paper. This is some random image from course. So I'm not sure whether these key points are real key points which will be detected by SIFT. So, but let us say these are but these images you can see from the on the left image and the right image are from the same scene, but slightly shifted, maybe not rotated, and there is no scale changes here. But there at least there is some translation here. So I think these are stereo images of two cameras. One is fixing, one is other thing seeing. So, but if you run any key point detector, it may detect some key points here and some key points here. Now, for example, these the points which are in red, uh, they won't have a good match. Why? Because you see the patch around these key points, these are not distinctive enough. This patch, for example, around this can land up to any patch around this. Okay, so first of all, your detector should not detect these as a key point itself. Ideally, it should not detect things, but you cannot avoid. You may end up getting some of those point problems, and in that case, the matching will always be ambiguous. Blue points, if you see these blue points, these are points which have a potential for good match, but in this case, those are probably not the correct matches. How you are, this is manually done. So probably these are not getting matched with the I think they used the SIFT descriptor or whatever, and then they tried to compare it and found out that these blue points were not they did not actually end up matching correctly. For example, this blue point may got matched with this one or something, and the yellow ones were which actually ended up matching correctly. So of course we need not to worry about red one, because most probably we'll try to get rid of these things through our good using a good detector and using these things. But to distinguish between blue and yellow means the ones which are good match still, but still if they ended up matching wrong ones, and which is possible. For example, if you see here, this wall is a different wall than this. So any point here ideally should not have any match here, but still because those are looking similar, those patch are similar, so it may end up matching some of these key points there. So that is a practical problem, which is not a problem of the algorithm itself. It is a problem because of the this is a practical problem which end up many times in computer visions. You have to deal, outliers will always be there, as we said, noise will always be there, outliers will always be there. You cannot avoid it due to n number of reasons. So how do you handle that? So in the SIFT paper, so in the next set of lectures that we'll talk about a more global approach to handle these things, seeing the entire distribution of data and using some parametric models and shape informations and all that. But today we are just going to see some local method which the SIFT used. So the local method which SIFT basically used was basically, so it said that one thing is this, we to see whether it is going to be a good match, not only the descriptor of the key point itself, but we can also do a simple sum of square difference between the patch around those key points. So we'll take a patch around that key point, another patch around key point, and see how close the template or the patch around that is how good that difference. If that difference of sum of square difference is less than a threshold, probably then it is a better chance to be a of a correct match. So we are not going to match, that means we are not going to, even though our descriptor may match, but we can add robustness to it by also matching the patch around that and do a sum of square difference between those, basically a template matching kind of thing. And until unless this itself is less than a threshold, we'll not say that it is a correct match. But how to set this threshold? So experimentally what they found, basically if they use the one the best so so this is this is the patch around the, so they basically found the, if you find the best closest match and take the patch around those and take this sum of square difference error and plot it on this direction, and this is the probability of density of the matching of the key points. So they have plotted these two things. One is correct matches and another is incorrect matches in the dashed one. So what it says basically, once this sum of square difference increases, then the correct matches, the density of the correct matches falls down sharply. Means, for example, what I'm saying here, that if it is going to be a correct match, this SSD value should be very low, which basically says that when the SSD value is quite low, our correct matches are high and incorrect matches are very low. But as we move, as the sum of square difference increases, the correct matches fall down and incorrect matches increases. So we can put a threshold. For example, if you put a threshold somewhere here, that means we say that SSD value should be less than 10, then we say that it is a correct match. Will that be good enough? With this threshold value, now through this graph we can set this threshold value. We are saying that this correct matches are falling down as we are going away. But as we see, the other problem is we cannot, although this is giving a quite a good idea of where to set the threshold, but still there is a problem here because that in this location even the incorrect matches are quite high. It's not too low. Even the incorrect matches, the distribution of incorrect matches is also quite high. So putting a threshold here or here is not, will not be a good idea, because within this you will also end up getting a lot of incorrect matches. So again they again use the same trick. Again they use the ratio of the sum of square difference between the first closest match and the sum of square difference between the second closest match. So first they use the ratio between the descriptor match itself. Now they are using the ratio between the patch around that key point match, and that ratio, if the plot, so now the x-axis is the ratio of this sum of square difference error. Now this graph gives us a better idea where to put threshold, because as we said again, uh, uh, when there is going to be a good match, the first value should be very low, and the second value uh, will be higher than the first value. So in that case, that ratio will increase. So as we see, when this ratio is low, the correct matches are very low. But when this ratio increases, the correct matches, oh, the correct matches are in the continuous line here. So when this ratio is low, the density of the correct matches is high, and then this reduces when this ratio decreases. And inversely, again the same argument will apply here also. If it is an ambiguous key point, or if it is a random key point which is being getting matched, then then the reverse thing will happen, and which is being shown here also. Initially these incorrect matches are low, and when this increases, the incorrect matches are high. So now this graph will give a better idea where to put threshold. For example, if you put the threshold around here, here the number of incorrect matches are very low, and mostly we have all correct matches. We can go a little further also, but still we find the incorrect matches are very less, and we are almost able to get 80% of the correct matches in that region. So if we put this threshold, we are able to get 80% of the correct matches and avoid most of the incorrect matches. And as we'll see that we actually don't need 100% matching, because the problem that we are trying to solve, so where we started, uh, most of the problems for example, when we are trying to do that alignment problem, we need only 4 or 5 or 8 correspondences. Once we need 8 points, we can know the transformation matrix, or 6 points we can know transformation. So out of 50 matches, if you are even able to get precisely 6 correct matches, then you will be able to estimate the transformation matrix. So we don't need all 100% matches, we just need few correct matches, but we should be sure that it is the correct match. Okay, so how did they set up these values, 16 bin orientations and all that? They basically did experimentation, extensive experimentation. So for example, if they use the 4 by 4 patch versus 8 by 8, no, I think this is the histograms. So the histogram finally, as they actually used 8 orientations in the histogram. So actually they tried with 4 as well as 16. With 4 the accuracy was much less, with 8 the accuracy actually increased, and with 16 the improvement in the accuracy was only marginal. So there are two parameters here. One is the n by n key point descriptor. So why they actually ended up using a 4 by 4 because after 4 by 4 the performance basically is saturated. As you can see, there is a plateau, so performance is increasing from one using 2 by 2 patch or 3 by 3 patch and 4 by 4, and after 4 by 4 the performance is getting plateaued. So they basically use a 4x4 patch. Similarly, this graph is basically showing the stability with respect to noise. And you can say even with up to 8 to 10% of noise addition, the features are almost stable. The correct match, the percentage of correct match does not degrade so much. It's almost similar. So this is a graph from the paper itself. So they basically these are patches basically from this image. So one patch is from, I think, somewhere from the heart. This is from the this tree, and this from the totem pole on this. But these patches are in have different orientation, different illumination, and so on. And they basically when they did their patch matching and all that, they ended up finding the correct location. In fact, they showed many such examples. They are able to match objects with different orientations and all that. So okay, we'll stop here. I will continue in the next class. Uh, so we have basically finished up discussing how to find interest points and how to describe them in a scale invariant as well as rotation invariant manner. And this feature detection and matching is actually has many applications, not only like object recognition, object detection, aligning images, in tracking objects over in a video sequence, and so on. So it gets extensively used, this fundamental techniques. In the next set of lectures, we are going to handle this problem of outliers, how to handle these outliers. So here we use the simple heuristic local method, but we'll see a more robust methods which is well founded on theory, which is kind of a global measure to do that in the next set of lectures.